Back for more. So we've got our NMR, our big things to glean from it. We've already addressed our number of signals, chemical shift, and integration. And now for multiplicity. This gets us a lot of information, but it is easy to get bogged down in the details behind it, so please be careful. I will also say that this video is going to pile on even more details that you thought weren't even there when looking at multiplicity. Okay, so this may not be one for the faint of heart. If you feel like you need that extra question, go for it. Let's see what we can do. So, the basic premise behind this. Hydrogens are magnets, and magnets can affect each other if they are close enough. Okay, so that close enough is what we refer to as the 3-bond rule. It's not really a rule, but be aware of it. So unequivalent hydrogens, so they have to be unequivalent, are neighbors if they are within 3 bonds of each other. Okay, so what this typically means is that if we were to go through and look at an individual sample, we might go through and say that the hydrogens on this CH3 are neighbors to these blue hydrogens. So if we were to count this out, okay, we'll count it out in purple. Okay, 1 bond, 2 bonds, 3 bonds, I've ended at a hydrogen. So that hydrogen is a neighbor to that one. If we were to count it out again, we'd see another one down here. That hydrogen is a neighbor to the first one. So right now we have 2 neighbors. Okay, let's go through in a slightly different color. Let's go ahead and pick orange because it'll be confused with the red. We go 1, 2 bonds. Okay, we're now at a hydrogen. Does that count as a neighbor? Well, remember, it has to be unequivalent. Those 2 hydrogens are homotopic. Yeah, homotopic was the right word, are the same, which means they can't act as neighbors. So the way I like to think about it is that if we were to look at, say, I don't know, your house and you are living with family, significant other, something like that, they wouldn't count as your neighbor, but the house next door would count as neighbors. Okay, so the people in that house count as neighbors. The next part that people often get confused with is they'd say, well, why does the second one count as a neighbor? Isn't it the same as the first one? Well, yes, but if you're having that relationship with, and be careful with that word, with the neighbors next door, you don't have the same relationship, say, with the wife next door as you do with the husband next door, right? Or for that matter, with their kid. You get a slightly different interaction. That slightly different interaction is manifested when we're looking at our multiplicities. Okay, and that's kind of the hopefully simple part of this. How does this kind of translate out for us? Well, there's another kind of thing that goes along with it, and we get n plus 1 equals s. So neighbors, or n equals our neighbors, and s equals our number of peaks. I've since switched to trying to make that a P instead of S for peaks. The S is a holdover from the term splitting. So you may hear me reference splitting and multiplicity. They are synonymous, so don't stress about that. Okay, so what do we mean by this? Okay, well, what we mean is exactly that. So if we looked again at that CH3 next to the CH2, and I wanted to know what did that red hydrogen turn into as a number of peaks? Well, as we addressed, it had 2 neighbors, so I could say 2 plus 1 equals the number of peaks, 3. And it would have 3 peaks. Okay? Those 3 peaks have a very characteristic shape. Man, this did not align nicely at all. 3, 2, oh goodness. It aligned better than I thought. I just did it wrong. 0 neighbors means 1 peak. 1 neighbor means 2 peaks. 2 neighbors means 3 peaks. So those 3 peaks that we're seeing are shown here in the boxes. Each of those boxes represents a peak. The number within it represents the intensity. So if we said that first one was an intensity of 1, well, the next one has an intensity of 2, last one 1. So we get this peak patterning for that. Each of these has that same kind of patterning associated with it. So we did the last one, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 1. So that would be for the last one. So if you note, you're seeing this kind of symmetrical pattern come out of this. Okay, and as far as splitting goes, it is mostly symmetric. So you should be seeing something along those lines with your peaks kind of symmetrically oriented. Good thing I didn't do that one right. Underneath that pattern. It's not 3 random kind of peaks or all increasing. It goes up and it comes down. Right? That patterning has to be there. And so that's what this diagram is attempting to show. There's a little bit more math associated with it that if you really wanted to, you could dig into, but don't stress about that. It's just trying to show those patterns. That's what we would do, okay? Well, why do we see all of those signals? Well, let's simplify this down a little bit and just say we have a single hydrogen, okay? No neighbors. With no neighbors, we really only get one signal. It's either oriented up or down. The absolute magnitude of that, though, is the same, so I get one signal. Well, what happens if I bring it near another hydrogen? Well, we could get the system where they're both aligned up. We could also get it where one is up and one is down. We could get the system where one is down, one is up, and if we erase that so we can see through this, and then down and down. Hopefully what you see is this one and this one have the same magnitude, opposite directions, but same magnitude. This one and this one, same deal, okay? That is one peak. That is the other peak. So it's just looking at all the possible ways that these things can combine. If we went through and did 2 neighbors, well, the same kind of thing is going to happen. It's how do we possibly align all of these things, and how do we get those individual intensities? The intensity, how many things did I highlight in green with that? There was 2, in blue, 2. So the ratio 2 to 2, integration 1 to 1. Okay, so that's kind of where it's coming from. Again, I don't want you to super stress on that. What you need to remember, unequivalent hydrogens, neighbors within 3 bonds, and then n+1 equals p or s, however you want to do it. Okay, those are your big things to pick up within multiplicity. There are all sorts of ways that things can go sideways, and you get little nuances, things to watch out for. And we'll take a little bit of a peek at that, okay? So we can encounter this issue of splitting of splitting, okay? So what do we mean? So let's not do the chiral one right away because that's just going to break everybody too fast. And let's do something like this. So we have a CH3, a CH2, a CH2, CH2, and our CH3. Okay, so hopefully you're comfortable with the number of signals, and we get 3 signals here. We could also go through and do the integrations, but again, we aren't stressed about that. We're concerned about our splitting. Well, what happens to the red one? Well, if we went through and looked at its neighbors, we're going to find that it has 2 neighbors. Those 2 neighbors plus 1 gets us 3 peaks. Okay, also known as a triplet, which is often abbreviated, it's just a T. Now let's take a look at the orange one, which in and of itself is going to be an interesting one. How many neighbors does it have? Well, it has 2 neighbors there and an identical 2 over there. Okay, so it still has to count them both, and we would get 4 neighbors. Plus 1 gets us 5 peaks, and that would be represented by a quintet. Okay, sometimes typically not actually shown as a Q because a Q comes in as a quartet. Okay, pentet maybe. I think that's actually it, pentet. Okay, what happens with the blue hydrogens? Okay? And this is the one that I think becomes the most challenging. The blue hydrogens see the red ones, and so have 3 neighbors. They also see the orange ones, which have 2 neighbors. In the case of the orange one, it saw 2 of the identical type of hydrogens causing the split, so we don't see anything weird. But with the blue one, we get orange and red, and those are slightly different, or at least here they're different colors, and that could contribute to what's known as splitting of splitting. Because the orange and red aren't vastly different, what you will oftentimes see people do is just say that this is 5 neighbors plus 1, which equals 6 peaks. And when we're going through and solving, that is mostly true. Okay? But not always. Okay? So what could happen out of this, and this is where we get the splitting of splitting, and it becomes ugly really fast, is that 3 neighbor turns into 4 peaks. Okay? So now what I'm going to do is draw that. So here's our 4 peaks, nice and symmetric. But now that signal sees the 2 neighbors, okay, the orange 2 neighbors. So that signal must now split into 3, okay, but it's already been split, so it splits again, okay? Nuts, right? So we got our quartet, and then we got our triplet. So what we could reference is our end signal looking something like that. That looks like a god-awful mess, and that really only works if our instrument has a strong enough magnetic field so that we can actually see those signals and resolve the signal. Typically what happens is that those signals start to overlap, and I'm going to delete everything because I think it's easier to see with my hands. Those signals would start to overlap with each other. And the instant those fingers overlap, that signal gets twice as tall. Okay? If they then overlapped here, now we get a big mess and it becomes hard to see. So what we would oftentimes see is just a mess, and we would call that a multiplet. Okay? If we're lucky, it aligns perfectly and we get that clean patterning that I think I suggested came out as a hextet, okay, with 6 peaks. Okay? So sometimes it works, sometimes it doesn't. Chiral atoms add a whole nother crap fest to this. Well, what do we mean? So let's take a look and apply that same content back to our chiral atom. We have our 3 hydrogens out over here. Remember, we had the chiral atom, which meant that these 2 hydrogens were different. Well, so now what happens with that red hydrogen? Well, that red hydrogen sees 3 neighbors, so we would turn into, a quartet. Right? 3 neighbors, 4 peaks. But then it sees that hydrogen, which is a little bit different. Okay? That's 1 neighbor, so it turns each of those into a doublet. But oh my God, it sees another one. You say, why on earth will we ever have to worry about this? It's a good point. This complex splitting is so complex and refined that the likelihood that we would ever detect that is slim to none. Okay, so we don't have to stress about those. But I want you to be aware that that is what's happening when we call splitting of splitting. So if I say a doublet of doublets, what we're saying is the doublet signal, but then it saw another one, which split again. So a single doublet means 1 neighbor. Another splitting means another 1 neighbor. So if I was concerned about this hydrogen and I saw this pattern, what that means is this had to be true. That red hydrogen had 2 1 neighbors. There's a 1 neighbor in blue and a 1 neighbor in green. Okay? That doesn't happen super often, but it can happen, and it is something that you should be aware of when and if it pops up. You will also hear reference to doublet of doublets in terms of aromatic rings. That is entirely a false statement. It is never a doublet of doublets when we're looking at aromatic rings. It's two doublets. Didn't doublet mean two? Doublet means very specifically the splitting. Two is now the number of signals that you're seeing. Okay? So be aware of that nuance. Where could we see that kind of goofy patterning happening? Let's look at another example here, which will be referenced on the very next slide. Let's do this. So a nice good old propene. How many hydrogens would we expect? You might go through and say, well, 4, because you colored them. Fair enough. Do you actually agree with that statement, or are you just making it up because I've put in those colors? Okay. The blue hydrogen in comparison to the red hydrogen, if we were to count that out, 2 bonds away. So 2 bonds away, it's within 3 bonds. Is it chemically different or identical? Well, the ring, or not the ring, the double bond prevents rotation, which means the blue hydrogen always sees the methyl. The red hydrogen always sees the hydrogen directly across from it, which means the red and the blue are indeed different. Okay. What does this mean for us? Well, this then means that we get to deal with all the splitting that would come out of this. Okay. We have one neighbor there, 1, 2, 3, one neighbor over there. Okay. So that blue hydrogen has 2 1 neighbors. For those of you saying, well, dang, isn't there the methyl? Fair enough, 1, 2, 3, but then what do you have to do? You would have to add one more bond to get out to that hydrogen. That would be a long distance split, and it can happen, but it is fairly rare. Don't stress about those. Okay. Oh my goodness. Okay. Last thing we kind of want to address, and you probably are already sick of this and 20 minutes in, which is probably 20 minutes longer than I wanted it to be. The splitting between that blue and the green is going to be different than between the blue and the red. Okay? And that's because those distances are different. Well, if we talk about splitting, the splitting is the gap between there. Okay? What is that distance between those two peaks? Well, it turns out because those are different splits, we get different distances. So we could measure that distance and say the relationship between those groups. Okay? And I know you're like, stop being excited. I can kind of understand that. Okay? But what we're referencing is what's known as the coupling constant. Okay? 2 hydrogens that see each other are coupled. That's what's causing that splitting pattern. The value by which they split we can use to give us characteristic information. So we could look at, say, the spectrum that we see down here, and we say, well, for this signal, it's split by 7.6. Well, if we look at the signals at 7, they split by 8.5, which means that signal at 1 is not next to the signals at 7. It has to be next to the signals. Oh, I got A, B, C, D. The signals at D are not split by A and B because that coupling constant is different. Okay? To get into that coupling constant, you really have to drill down, and I don't ask questions like that on an exam. But on homework, absolutely is fair game. So if you're seeing those values, sorry, that's what I'm asking you to do. You have to dig into it. Okay? And ultimately what you would be doing is looking at a table. I don't expect you to memorize this. You'd look at a table and see what that coupling constant was. Based off of that value, you could then define the relationship between those hydrogens in that and nail down the overall structure. Whew. That was a lot. I apologize for 20 minutes of brutality, but at least we're done with that.